Hey everybody, last chapter, chapter 11. We're going to learn about one more distribution, chi-square. Let me tell you a little bit about it. Okay, so what's going on here? This is a non-symmetrical, skewed to the right type of distribution. We're going to use it in certain instances that I will tell you about. It's a little bit like the t-distribution in that we're going to use degrees of freedom and that there's kind of a different curve or chi-square distribution for each degrees of freedom. We're going to calculate a test statistic, and what's weird is it's not a z-score, it's not a t-score, it's chi-square, which is like a fancy x, you'll see it, and it's always going to be positive, it's always going to be greater than 0. That isn't the case, right, with z and t, because we had a symmetrical bell-shaped curve. Here, if you look in the book and the slides that are in the files, it's more of like a mountain. It's all to the, it's all on the positive side of the number scale of 0. The other thing I want to tell you is that when the degrees of freedom get really big, meaning that our sample size is really big, chi-square does approach a normal distribution. Okay, so those are the basic characteristics. We're going to do a couple of different kinds of tests. The first type is called a goodness of fit test, and that is when we see if the data fits a particular distribution or not. Usually it's always going to be right-tailed, and what we're doing here is we're going to compare observed values, which are the O, to the expected values, which are the E. And we're going to see if the observed fit the expected, and we do it with a test statistic that I tried to calculate or put in here as sigma, right? We add up all the differences in the observed minus the expected values squared, and then we divide it by the expected. So we have some calculations to do. I can show you how to do it on your calculator. We create a matrix. You know, it's really a pain. I'm teaching you this because I want you to know it. We're going to do baby steps on this. And then if you go on, or when you go on in statistics, just know you'll need to look this up a bit more, but we'll practice it. Okay, so what we do is just like with any test, we're going to set up a null, we're going to set up an alternative, and in this case we'll always use words. The null hypothesis, the population fits the given distribution, our observed equals our expected, in other words, and then the alternative hypothesis, the population does not fit. So that would be like an equals with a not through it. So that's a little bit like our chapters 9 and 10, you know, setting up our step 1. So let's do this. Let's draw a conclusion about whether two populations have the same distribution. This is a different type of goodness of fit test. We call it a test of homogeneity. So now what we're trying to do is not just see if the observed or expected are the same. Now we're going to see if they're just the same distribution in its entirety. So it's a little bit of a different flavor of this. So you'll see it as the two populations are the same, the two populations are different. Again, we're using chi-square. All right, let's go through an example. So let's do one of these tests of homogeneity. See, an employer wants to know which days of the week employees are absent in a 5-day work week. Suppose a random sample of 60 managers were asked on which day of the week they had the highest number of employee absences. You could see how this would be good for budgeting, things like that, staffing. The results are shown here. So I've got this little chart I tried to put together. So for the population of employees, what we want to know is, do the days for the highest number of absences occur with equal frequency? Let's see. So we're going to test it at a 5% significance level. That's our alpha. And so here's what we observe. We have 15 absences on Monday, 12 on Tuesday, 9 on Wednesday, 9 on Thursday, 15 on Friday. So that adds up to our sample of 60. That's our observed. What would our expected be? Take that 60 divided by 5 days of the week. We would expect there to be 12 every day if it was just equal. So here's what we do in words. We have our null hypothesis. The absent days occur with equal frequency. They fit a uniform distribution, however you want to phrase it. The alternative hypothesis is that they are not occurring with equal frequency. They don't fit a uniform distribution. So our expected values are E. That's the 12, 12, 12. You can see it down here. And then the O, the observed values, that's what was given. Monday was 15, Tuesday 12, etc. So now we could do a chi-square test. And we have to do it by hand. Unfortunately, not really easy to do. I mean, we could do it with a matrix, like I said. So let's just do it. Let me show you it. How do we do that? There's the chi-square, right? This is a little bit like our z-score and our t-score. This is our test statistic now with a different distribution. So what we're going to do is we're going to add up each one of those O minus E's squared and divide it by E. So if you think about it, we would take, let's go back for a second, we would take O, 15, minus E, 12, that would be 3. We would square it, and then we would divide it by E, 12. And then we would add it with 12 minus 12. That's O minus E squared. 0 squared is 0 divided by 12. That's 0. Then we would do O again. We're adding all this up. 9 minus 12 squared divided by 12, etc. And if you do that, what you'll find is that your chi-square statistic is 3. Okay, so we want to find, just like think about those steps of a hypothesis test. We've got our null and our alternative. Then we know our alpha, it was 0.05. We just calculated our test statistic. In this simple example, it's 3. So now we want to figure out the p-value. What's the probability of getting that test statistic, a chi-square of 3, if our null is true? So we are going to use our calculator for that. And we can figure out that our calculator gives us a p-value of 0.5578. You need to know the degrees of freedom to do this. Degrees of freedom are always the number of cells minus 1. In this case, we had 5 days minus 1, so we have 4. The p-value is so large, right? It's greater than our alpha. We will not be rejecting the null. So how do you do this? You're probably wondering, oh my gosh, how do I do this on my calculator? Okay, it's a pain. So how you do the test statistic is we've got a 2 by 3 matrix, right? We have our observed and our expected. Those are our 2 rows. If we were to do it by 2 by 3, let me just say. So we would go to matrix key, and we would arrow over to edit, and we would press enter. We would press 2 enter and then 4 enter, and that's going to give us our table values. And every time we get to the table value in our calculator, we're going to enter a statistic, enter a statistic. Then we're going to quit. Okay, that's how we create our matrix. And so this isn't for our example. Sorry, I apologize. This is if we're just doing a simple one, 2 by 3. We could do a 2 by 5 if we wanted. So let's say then we go back to do our test. You do stat, you arrow over to test, you arrow down to chi-square test. You'll see it. So once you have the matrix put in there, which is the observed and the expected values, you have to do the data entry, then you can just do a test. So that's one type. Okay, and so with the p-value, sorry, I should just close this off. Let's go back with the p-value of 0.55. That's so large, like I said, we are not going to reject the null. Let's go back and see what our null was. Our null was the population fits the given distribution. We do not reject it. So it's possible that it could fit. Okay, there's another type of test, and this is also using the chi-square, and this is when we do a population variance test. So up until now, we've been doing tests about mean, and we've been doing tests about proportions. Now we can actually do it about a variance as well. Okay, again, sadly our calculator doesn't quite always help with this. We're going to do our test steps just like we would, a null and an alternative. We could state them in terms of a population variance. So it might be that the variances are the same. That would be our null. Variances are not the same. And then here's the formula for calculating our test statistic. We would take n minus 1. So that's just our sample size minus 1. Then S is our sample standard deviation, we square it, and then we divide it by our population standard deviation. So this is a simple, we don't have to do a matrix for this one, it's a really simple way to calculate a test statistic. And I've got here what those things are, and we might have a right-tailed test, a left-tailed test, a two-tailed test, depending on what we want to say about the population variance. Let's go through a little example here. Population variance, let's say Buyer's Digest is rating Thermarite thermostats, and it gives an acceptable rating to a thermostat with a temperature variance of 0.5 or less. Okay, so again, we're not going to use z-scores, t-scores, and all that because we're talking about the variance in the temperature. That's what we're testing. That's why we have to use chi-square. So we conduct a hypothesis test. We have an alpha level of 0.10, and we're going to determine if this variance is acceptable. All right. So here are the readings that we get in a thermostat. Oop, I can tell that this is going to be hard for you guys to see. Let me see if I can pull this up a bit. Oh, I know what I can do. There we go. How about that? So we've got 10 readings, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops, this is a little bit off, but thermostat 1 has a temperature reading of 67.4, the second time 67.8, etc. So we want to know if it's an acceptable variance. All right, let's do our test. Right? If it's too big of a variance, then maybe this temperature thermostat, isn't working very well. All right, so let's say that we have, remember, this is variance, it's standard deviation squared. We have a right-tailed test because we want to see if it's greater than 0.5 of a variance, and that goes immediately into our alternative hypothesis. That's what we're testing. So we want to know if the variance is going to be greater than 0.5 degrees, and then, of course, our null is mutually exclusive, less than or equal to 0.5. So we're going to do the same thing. We've got our null. We know our alpha level. It's 0.1. And then we calculate our test statistic, and then we're going to see, is the p-value, the probability of getting that test statistic, if it's greater than alpha, then we will reject. If it's less than alpha, we do not reject. So how do we get a p-value once we calculate our test statistic? It doesn't come out like it does when we do our z-test and our t-test. We have to go to second function distribution and go down to number 7 and look for the chi-square distribution. Remember way back when, normal CDF and binomial CDF, all that? You're going to do chi-square CDF. And the syntax, the way you put this in is you're going to do lower bound, upper bound, and degrees of freedom, and that's how we get the probability of getting that test statistic. And then we compare it to alpha, see if we should reject. So here's our test statistic calculation, step 3. Chi-square is going to be n minus 1, right? We had an n of 10, so 10 minus 1 is 9, times the sample variance, which I calculated. Do you guys remember how to calculate that? You go to stat, edit, list, put the data in, one variable, statistics, and you get out all the good stuff. So I calculated that variance as 0.7, and then I'm dividing by the population variance, which is what was given to us, 0.5. So my chi-square test statistic is, let me move myself here, 12.6, and then I did that thing where I went into the chi-square CDF distribution, and I got a p-value of 0.18. That was the probability of getting a chi-square test statistic of 12.6 if the null is true. And guess what? 0.18 is not less than an alpha of 0.1. So there's insufficient evidence. We cannot conclude that the temperature variance for thermarite thermostats is unacceptable, right? We cannot, let's go back to what our null is. Let me find that. Blah, blah, blah. Okay, I'm way out of bounds here. Here's our null. Our null was that it was less than or equal to 0.5, right? So we could not. There's insufficient evidence to reject. All right, everybody, that's it for a quick tour de force of Chapter 11. Email me if you have any questions, and the complete set of the slides is in the files. Thanks.